So nomenclature, we got an online video on that. I am jumping the gun a bit on the nomenclature activity or the nomenclature teaching aspect of it. So there is some material in there that you're going to have a little trouble with because we talk about charges within that. And we don't quite have a concept of charges yet, but there are tables in your textbook that tell you what the charges are. So you may not need to know exactly what the charges are, but you have an idea of at least on where to find them, and you can start to work questions based on it. When we look at our nomenclature, we're dividing it into separate categories. You really only have two categories. It's really ionic and covalent. And they have different sets of rules for them. Your ionic compounds, we're going to specify charge. So that needs to show up in the name. And we do not say anything about how many of each of those elements are present. In the covalent compound, now what we do is specify how many of each of the elements, but we don't say anything about charge. Okay, so they have kind of reverse notations with them. And this has to do because the bonding nature in each of those compounds is drastically different. So we have to come up with different ways to name those compounds. The acids are kind of an afterthought of the ionic compounds. They're a special case. When a particular type of compound is dissolved in water, it generates the characteristics for an acid. Okay, that's ultimately the hydrogen. So we've got a real brief, quick summary of all of the nomenclature video written up here. Okay, on the quiz we just did, we asked about, excuse me, that was weird. I have no idea what that was. What did we ask, actually? I don't remember. Provide the formula for magnesium chloride and the name for S2O7. So our formula for magnesium chloride, that will classify as an ionic compound. From the lecture video, an ionic compound is a metal and a nonmetal. You should be able to classify these according to ionic and covalent already because you know metals and nonmetals. The symbol for magnesium is? Mg. I know it did that. Let's come back there. It's Mg. Symbol for chloride? Cl. Minimally, you should be able to pick that up. Fortunately, that's not the correct answer. Okay. The correct answer has to do with the charge on each of those atoms. Okay. And if you knew the charge already, great, that's fine. I'm not penalizing you, so don't panic on this. The charge on magnesium happens to be a +2. The charge on chloride happens to be a -1. When we go through to build our compounds, they will always be neutral because neutral is our lowest energy state. If we put together one magnesium and one chloride, what would our overall charge be? A +1. That's not neutral. So what do we have to do to our formula to make sure it comes out neutral? I need a second chloride. So one option would be MgClCl. Okay? It could be a bit repetitive, particularly if we move to our next compound, which was S2O7. Okay? But we can abbreviate and switch that to Cl2. So now the question is, where do you put the 2? We go to the bottom right. Okay? So we have magnesium chloride. Why do we not put it out in front? It looks kind of weird out in front and applies to everything after it. And if we put it directly in front of the Cl, it kind of confuses things as well. Okay? So we're trying to get it in a location that is as minimally confusing as possible. In this case, it just happens to be that lower right-hand corner. So we now have our formula for magnesium chloride. Pretty cool. You'll notice that I'm not specifying the charge. Why not specify the charge? We will only specify the charge on the cation, or positively charged species. Why am I not, or wait, yeah, why? Yeah, sorry, I'm thinking the reverse. We won't need to specify the charge in our formula. We only specify the charge in the name. Okay? So since we were given the name, we don't have to worry about the charge. Why was the charge not given to us in the name? Okay, there are certain elements that you are required to know the charge for. Guess what magnesium is? One of those elements. If you're required to know the charge, then anytime you see magnesium in an ionic compound, it will always have a +2 charge. Well, if it always has a +2 charge, why bother to write it out? Okay? It just becomes a bit redundant. The next one was naming. All right, S207. If it wasn't that, it's that now. Okay. In this case, we have two nonmetals, so we can't name it under the ionic rules. We have to go through our covalent rules to go through and name this. We'll list our first element name. The first element that shows up is sulfur. The second element that shows up is oxygen. You'll notice that we change the ending of the oxygen a little bit. It becomes our second element. We change the ending to "ide." Okay, this is not super intuitive. It kind of goes based on what sounds good. Okay, so it's not oxygen-ide, it's oxide. We run into another issue here. You notice that we've got these Greek prefix statements. What are those in reference to? The amount of each of those species. So we need to know the Greek terms for the amounts. The Greek term for 2, di. So it is disulfur. And our Greek term for 7, hept. So we'd have disulfur heptoxide. There's our name. It is not sulfuric. Sulfuric only shows up, that ic ending shows up when we move into acids. We're not an acid. And yes, we'll layer that complexity on once we got a little bit more going with it, but first we'll stick with kind of the simpler ones. Okay? Questions about either of those two? Okay, now a depressing question. How many people watched the video? Well, that wasn't too depressing. That's not too bad. Okay? So you should go through and watch that because that's going to be your primary information for nomenclature, that and the chapter. What we'll do in class is just periodic, hey, let's name this, let's name this, let's name this. You'll get a lot less of the detail on how you go through and do each of those naming things. There is a lab, I don't know which lab it is, but there is a lab that I believe shows up before exam 2 that is strictly nomenclature. You go in, you sit down, and you do 100 naming problems. Okay? It's super exciting. Okay? If you're good at nomenclature, what you should do is do that now, because then when you come in, you sit down and say, okay, do the assignment. You give them the assignment. You say, well, what do you want me to do now?
Go home.
Yay, go home. It's nice. And that sets you up with the practice that you need for the exam. Okay? So just thinking about that, throwing it out there, just give it a thought. It's in your packet. It's in your lab manual packet. I don't remember. It's probably lab 5 or 6. Okay? So I would highly encourage you to take a look at that and start working those problems. If you've got questions about it, feel free to ask your lab instructor. Feel free to ask me. We'll help you through with it. Okay? He does have the right, by the way, to actually keep you in lab doing something else. Very few instructors have enough practice to keep you in lab if you finish all of that practice. Okay?
Would you do that, Tom?
I can't answer that question. One of the other things that's going to pop up, you'll notice that with the acids, we say binary acid and ternary acid. Those of you that watched the lecture video already on nomenclature realize that in our ionic compounds, we have binary ionic compounds and ternary ionic compounds. Binary stands for 2. We're just looking at 2 elements. Not the amount of each of those elements, just 2 types of elements. If we have just 2 types of elements, we're going to be binary acid or a binary ionic. What does it mean to be ternary? Okay. We could go with 3, but it's really just more than 2. So if you have more than 2 elements, you're being classified under that ternary category, and you're going to run into a subject known as complex ions. Your textbook has a nice table that has a big list of ternary ions. Okay? You are responsible for knowing those ternary ions, what their formula is, and their name, and their charge. Okay? There's an awful lot to go through and deal with that. If you move to the tutoring center, which the tutoring center will give you lots of practice with naming as well, they have a nice little handout that goes through and gives you kind of another fully extensive polyatomic ion charge thing on nomenclature. I will warn you that that assignment or that little activity that they've designed is designed for all of general chemistry, including 151 and 152. They have slightly more to work with. So you may see some symbols show up that you don't recognize off of our table. Okay? So within your textbook, you've got this nice little figure that gives you all these complex ions. I would argue that a large percentage of those you will not see, okay? Which means it does not make any sense to waste your brain power memorizing that specific ion. Okay? So what ones might be useful to memorize? The purple star is a good place to start. Okay? It should be purple. It's supposed to be purple. Okay. Those purple stars are ones that I think show up extremely commonly, okay? And you will continue to see them throughout your career in chemistry, or if this is the end of your career in chemistry, then you'll still see them for the rest of the semester. So you should memorize those starred complex ions. Their formula, their name, and their charge. You need to know all three. Okay? Questions? Yes?
Will we be tested on the ones we're not supposed to memorize?
You are officially responsible for all of them.
So you could test them on them?
I can test you on the other ones.
Will you test this third time? Because I'll cut that question out and throw it in.
How about this? I will dodge that question by saying you are responsible for all of them.
Are you going to go over say the AQ stuff? Because I didn't understand that at all. It was like the end of the slides. Like after them it said AQ.
AQ. Oh, sorry, AQ. I got you.
Yeah.
AQ is a reference to our acids.
Okay.
Okay. AQ just means aqueous, which anybody, what is that, Greek, Latin, something like that, means dissolved in water.
Okay.
Okay. So your acids are a special class because it's not the pure compound, it's the compound. When it hits water, what does it do? And it does some very particular chemistry. Because that chemistry is so different than the other compounds, we call them acids as opposed to those other things.
Okay.
Does that kind of make sense? So that's all the AQ means. So if you see AQ, immediately that means you have acid. Okay, at least at this point. Okay? So, back to the fun stuff. Isotopes. Our protons are defining our element, and our neutrons define the isotope, okay, ultimately the mass of the element. So we went through and took a look at this. Atoms of the same element can have different numbering of neutrons. Okay? If they have a different number of neutrons, we can't call it a new element because the element's still the same, because it's still hydrogen, okay? But it has a different mass. That mass is now a property that changes, so we can refer to it as an isotope of hydrogen. For some of the really common isotopes, they get named. Hydrogen being the simplest element tends to be studied a lot, and we end up looking at hydrogen that we're typically used to referencing with just one proton as protium. If we have a neutron added to it, it becomes deuterium. If you had two neutrons, it becomes tritium. Okay? The DEU stands for 2. The tri in tritium stands for 3. Okay? You're not ultimately responsible for those. I just want to make sure you know where they're coming from. Theoretically, there's a 4. I haven't heard of one being used. Okay? So we already did that example. Do we need to do that example again? Okay, no problems with, okay. Okay, so we can go through, we got lead, E2, all that fun math. So where I want to get to is now the simple and weighted averages. Okay, this is a tricky concept to go through and do, and we did an example problem with it. Okay, but what I've now gone through and done is switch the question around to give you another format, another way that I could ask this question. Okay, so by increasing the ways that we could ask it, you now, in theory, become more likely to be able to answer it. So what we're looking at within the weighted average is taking our value or our mass times the percent. Okay, how much of that exists? Okay, plus the mass of the next one times its percent, how much of it exists. And theoretically, we can continue to do this with all of the isotopes for an individual element. We add those all up, and we'd get the numbers reported on our periodic table. Okay, so our periodic table just gives us the average mass. There are some isotopes or some elements that have really only one isotope. Okay? Hydrogen's a pretty good example, because when we look at the mass for hydrogen, it is darn close to 1. So most of our elements that are very, very close to an individual number or a whole number really just have one common element or one common isotope. Okay? But some of the other ones have a large variation. So we could look at titanium, 47.87. It's kind of close to 48, but we've got a little bit of variation there. That means there's probably some common isotopes for titanium that shift that mass off. Okay? All of those masses come back to this weighted average concept. Okay? So let's take a look at a new question that we could ask. Okay, the information given would be gallium has 2 isotopes. One of the things we are assuming in answering this is it only has 2 isotopes. We have gallium-69 with a mass of 68.926 AMUs. Okay? Do you need to know what an AMU is? Not really. All we need to know is that it represents mass. Okay? And I'm going to make the argument that you should really kind of ignore AMU because we shift to much better units later on in the semester, and AMU is pretty meaningless. Right? So gallium-69, 68.926 AMUs, and it has an abundance of 60.11%. Gallium-71 is our other isotope. What is the mass of gallium-71 in AMUs to 4 significant digits?
I was just going to ask, does AMU just mean atomic mass unit?
Yes. What does that mean as far as you weighing anything out? Nothing. Okay. It is an atomic mass unit, but you have nothing to tie that to. So, I'll give you a little bit of time. See what you can come up with here for figuring out what the mass of gallium-71 in AMUs is to 4 sig figs. This is a challenge. This is a complete spin off or a complete flip off of what we did yesterday. Okay, so you could cheat and look at yesterday's notes. Don't do that. Set up the work. So, do we know the percent for A? It's the 60.11. So we can convert that into a decimal. Do we know the mass of A? And we're going to be obnoxious. We can throw in the AMUs. Plus, now we run into an issue. Do we know the percent of B?
Yes.
Ooh, there's a mix of yeses and nos.
Yes.
Okay. Why do we know the percent of B? There are only 2 isotopes. So if we add up all of our isotopes, what should our total percentage be? 100%. So how can we figure out the percent of B? Well, we take the percent of A plus the percent of B, and that has to equal 100. So I'm going to trust you on that number. We get 39.89.
Yeah, 39.
39.89%. So, oops, that should be in purple. We're going to color code this nicely. Because I know you love color coding. And now it's 3D if you look in the right glasses. Thank you. That was, jeez, guys, this thing on. 0.3989% B. Next hiccup. Do we know the mass of B? No. That's actually what we're solving for. Okay, so we shouldn't know that. That's okay. But now we got equals average mass. We told the average mass. What do you mean yes? As chemists, guess what is always posted to our walls? A periodic table. And what does the periodic table tell us about gallium? The average mass is 69.72. Can you solve for B? Now it's just a question of your algebra, subtraction, division, and we can go through and solve for B. In theory, by guessing at the size of those numbers, I'm going to guess B came out to 70.9 and change. Really?
Yeah,
Oh, wow.
that's pretty good.
70 point, you said 92? And we got our 4 sig figs right there. So actually, there we go.
Average mass being should we make it the decimal?
I'm a little bit confused. What do you mean? The average mass is a decimal. We're not saying it's not a percentage. Yeah, so it's not a percentage. We have to keep it as exactly 69.72. Okay? So the way we solved it before was just going straight to what the average mass would be. But the average mass in a calculation is already given to you. It's on the periodic table. Right? So the way that we would most likely ask this is in this fashion, where we drop in an isotope. How else could we ask? I see your hand. Just give me a sec. Instead of asking for the mass, I could ask for, how about the percentage? Why not just ask the percentage? Which would be a sneaky kind of mean question, because you'd have the percentage really quickly and you don't have to do any of the rest of the calculation. Right? But if you're locked into, oh, I must solve all the way out, one of the answers that I would probably include would be the 70.92 along with the 39.89%. Right? Do you know what you're solving for? Not just I'm blanket solving all the way through. So be careful to answer the question asked, not the one you want to answer. Yes?
It should be 0.93.
Okay. Oh, I'm hearing some no's. Okay.
There's 4 sig figs, right?
Let's get our 4 sig figs. We got 0.922.
1.6.
I heard a 925. If we got a 925, 5 adds 1. Our answer should become our 70.93 AMUs. Okay? Questions? Okay. This type of question does show up on the final once. Okay? So I wouldn't stress too much on it. Figure out what you can, do what you can. You might see it show up twice on a standard exam, on exam 2, but once for sure on the final. Okay, you're looking at a concept like this. Okay, so you are responsible for it, but if it's something that's driving you up the wall you can't do, hey, one question. Let it slide. Okay? I have faith. We can move to heavy water, just kind of a random. Your textbook throws these in here. I try to delete them, but I guess this one I decided was actually kind of cool. We can look at this concept known as heavy water. Well, all water weighs the same, so how do we get heavy water?
With more neutrons in that.
We have more neutrons in our structure. And ultimately what we're saying when we have heavy water is instead of it being H2O, it's D2O, where the D stood for deuterium. Okay? So our heavy hydrogen. Right? So that's how we get this heavy water. Yes?
Isn't it like in the Dead Sea, so salty or something, you can just lay on the water?
True, but that doesn't have to do with heavy water.
Yeah.
But that's...
There's like a connection there.
No, the Dead Sea is a lot of salt in it, which ups its density, which means you can kind of float on it a little bit easier. Okay. So deuterium, D2O, it's a common process. A lot of people like to use it as a solvent for individual scientific techniques, which you won't see in this class. One of the interesting aspects of this is because deuterium is not the most readily available, you have to isolate deuterium or heavy water away from regular water. To go through and do that, it's not that difficult of a process, but you can just kind of siphon it out of big vats of water and eventually pull out all the deuterium or the deuterated water, and you have heavy water. You can then sell the heavy water to science facilities that actually want to use heavy water. So it's actually something that I've been told, though I've never tried to do it. It's simple enough that you could do at home and you could run your own little side business of making and selling heavy water. Yeah. Heavy water exists everywhere. It is in your water to a very small percentage. Other questions? It tastes the same. So after that, what we're going to do is jump into chapter 5 to look a little bit more at our periodic table organization. So there's a lot more scientists listed off on the top of this for our classification of our elements. I guess I personally am less interested in periodic tables organization than I am in atomic structure, so I know a lot more about atomic structure, and I think those scientists are kind of cool. When it comes to the periodic table, they did some cool stuff, but we've changed so much from their understanding that it's not that big of a deal to look at. So in 1829, you've got this guy, Dobereiner. Did I say that right? That's sure. Who noticed that there were patterns of the elements that they had found already. And in those patterns, they noticed there were sets of 3. Okay, so he had triads. And within those groups, they had very similar properties. So they could start to do some kind of predictions, and they could start grouping out their elements according to that. Okay, so that was kind of a neat little observation to make. In 1865, after we actually upped the amount of elements that we were aware of, the triads didn't work out quite as easily. We didn't see these groups of 3. So Newlands went through and said, actually, I think groups of 7 makes more sense. And so he built his own periodic table with groups of 7 as opposed to groups of 3. And he referred to this one as the law of octaves, which goes back to music. And one time long ago, I'm going to walk over here. And it started to move again. Was our law of octaves, and that's kind of what he played around with. Man, it got a lot more excited, didn't it? So that's kind of happening within the historical aspects of our periodic table. Where this became super important was with Mendeleev. He proposed that our properties were dependent on other things, okay? And so he started to arrange them according to atomic mass. Okay? With this atomic mass, he then designed his own periodic table and started to classify and noticed different patterns that came out of it. So if you go through and take a look at, say, his first column, column 1, and compare that to our first column on our periodic table. Go ahead, compare them. Those are pretty darn close to the same. It's not perfect. We got gold at the bottom of his column 1, and we definitely don't have gold on ours. Okay, but they're pretty darn close. He kind of worked with this, and because of this, kind of designed and organized his own table, and we kind of give him credit for most of this. The other things that he added to it was that he noticed that compounds within the same column reacted the same with oxygen, wherever it went. Okay? So you'll notice up at the top here, you see this RO notation. Well, that RO is just saying R for whatever element in that column and oxygen. So in that first column, there are 2 of whatever elements in that column when it reacts with oxygen. So if I wanted to look at the compound of copper and oxygen reacting with each other, the result I get is Cu2O. That's what his table is trying to give us. So he's got a lot of kind of cool information off of it. It became super helpful. We further refined it and kind of built from it. But neato. Okay? One of his biggest accomplishments was really the ability to predict new elements. We've already had a few questions about what can we do to we can get bigger or bigger. Okay, we've kind of hit our limit on nuclear size. The glue now falls apart with our nucleus. But if we think back to Mendeleev's day, we're only looking at maybe 50, 60 elements. If we got 50 or 60 elements, where do the rest of those come from? Right? Well, Mendeleev was actually able to predict the existence of these elements without ever having seen any evidence of them. Just by looking at his periodic table and saying, hey, there's a gap. What was that?
I thought I felt from my leg.
So there are gaps in our periodic table. Everybody watching at home is going, what are you laughing at? There are these gaps. And so what he was able to do was start to predict what things would fill these gaps. Okay, you'll also notice not only do we have that gap, but he's got these things in here called eka. Those ekas were his actual prediction. Okay, so he's referring to those as eka, and then he'd follow it up with aluminum or titanium. So that first one in the upper left, we've got eka aluminum. Why? Because whatever this element is related to the element above it. Okay? So he was able to see these patterns and kind of come up with some predictions. So if we go ahead and take a look at one of his big discoveries, we can take a look at germanium, which he called ecosilicon. So we didn't know what germanium was. We didn't have that element to actually evaluate any of its properties. But he went through, based off of his understanding of that column, and made some predictions about it. So we've got color, we've got atomic mass, we've got densities. So everything on this left-hand column under ecosilicon is what he guessed. If you compare that to what the accurate answer is on the right, it's pretty astonishing how close those matched. Okay, so the organization behind the periodic table really drives off of this. We can see these common patterns coming out of it, and you can come up with these predictions. So one of the reasons why our periodic table is exceedingly powerful when it comes to chemistry. We got lots of information stored in there. All we've got to do is kind of needle that information out of it. Okay? So kind of a neat process. And no, it wasn't perfect, but it's darn close. Like very high. It's always good to be super accurate. We can then move to this idea of individual families, and we can come up with different names, which I believe is actually okay, it's not the next slide. We've got helium, neon, krypton, xenon, and radon. We're kind of one of our last elements to be discovered. Those are kind of our capstone on our periodic table on the far right. Okay? These were kind of neat and took a little while to discover because they do not react with many things. Okay? They're very inert. So that's what inert means. We're just not very reactive. Right? So with this discovery, Moseley then further developed the theory of our periodic table to organize instead of by atomic mass, but based off of the nuclear charge. Okay? Which is why when we look at our table, it goes from hydrogen to helium, 1 to 2, but your mass also goes 1 to 4 as well. If we jump around, where's the exception? There's one, selenium and bromine. Take a look at the mass as we move from selenium to bromine. What happens to the mass? Nope, that went up. I should get my eyes checked. The one below it works? Yeah. Tellurium to iodine. 127 to 126. If we go based off of atomic mass, iodine should show up before tellurium. Okay? If we go based off of atomic number, tellurium comes first. Okay? So the atomic number was a much more reliable predictor of both reactivity and some of those physical properties than the atomic mass was. Okay? And that's because ultimately they're related. Okay? And that's why it took a little while to kind of nuance which was more important. Okay? Yes?
Off subject, but
That's what this class is about.
There's only a limited supply of helium,
Yes.
and that's why a big movement to outlaw the usage of helium
Yes.
and whatnot.
Helium is only synthesized in the sun. So we have a limited supply of helium on the planet. Eventually helium will disappear because it's less dense and it will float out into our upper atmosphere where we can't get access to it anymore, and we're then out of helium. And then no more balloons. What actually makes that a little bit more sad is that helium is used in its liquid form as a supercoolant. Okay, in its liquid form, its temperature is like 4 or 5. Oh no, that's solid, I think. Maybe it's 4 or 5 degrees Kelvin. Okay, so you're looking at negative 270 degrees Celsius. It's really, really cold. And when things get that cold, a lot of their properties change, particularly their electrical properties and their magnetic properties. So we use helium to actually cool a lot of our instruments, or some of our instruments, because that gets us to the proper magnetic strengths that we need to actually observe certain physical, structural things. Okay. So it is really important. ASU has a, how expensive was it? I want to say tens of millions of dollars for a piece of equipment, and it is cooled yearly on a budget of several $100,000 for helium, for liquid helium. It's also really funny if they put the wrong thing in, like you try and put liquid nitrogen in. Well, if there's liquid helium already in there, the liquid helium is significantly colder, and it causes the liquid nitrogen to freeze. Well, if your input freezes over, you now have a closed system with a rapidly expanding gas. So you've taken a multi-million-dollar piece of equipment and turned it into a very expensive bomb in the middle of ASU campus.
Sweet.
It was entertaining to be there, to say the least, because it wasn't my fault. I was there. Yeah, it was entertaining.
How is that problem solved?
Blow dryers. Lots and lots of blow dryers. Yeah, it was pretty classy. So we've got our lovely periodic table. And this is what we see and manipulate and use every day. So when we talked about the relationships between metals and nonmetals, that also kind of comes out of this atomic organization, okay, based off of those atomic numbers. We've got different groups within this, and we'll keep referring back and forth to these groups. They usually get different names associated with them. I know, surprisingly, no, actually I was going to say I knew them all, but that's not true. I always get the alkali metals and the alkaline earth backwards. I can never keep those straight, no idea why. Okay? But that's our column 1 and column 2 elements. So sometimes you'll hear a question, okay, what's a common property of the alkaline earth metals? Well, if you don't know where the alkaline earth metals are on the periodic table, that makes the question very, very difficult. Okay? So you do need to be familiar with these names. You don't get explicitly tested on them for the most part. They do pop up every so often. The transition elements are kind of this subsection on the inside. And we reference it as the inside because it is sort of actually on the inside of the larger group. Okay? And when we look at our electronic structure, we can further evaluate that. You then move to your right-handed section, and you've got, nope, don't remember those names, or those names. Pnictogens, chalcogens, halogens, and noble gases.
I can't imagine why you would get some of these names.
Okay. Pnictogens. I got it spelled, I think, on the next slide. Okay. The noble gases and the halogens, absolutely you need to know those references because those are going to pop up all over the place. Okay. The noble gases, you pretty much just remember as they just don't do anything. They're noble. They're inert. They don't do anything. It's that last column. That one's not that difficult to kind of pick up. The halogens are a little bit more difficult to memorize, but that is that next column over. Yes?
Is there so many variations of periodic tables and different information that would permit us to have some kind of printouts of varied periodic tables?
No. So on the exam, you get the same periodic table that you saw on exam 1. It's that same thing all the way through. Okay, that just makes it easier to go through and see things. The extra information is stuff that you would have to know how to layer onto it. And there is more information than you would think stashed already on that periodic table. The names of each of those, what do we call them, families? Yeah, our families of those individual columns is kind of a secondary point. It's not that big of a deal. If you want to spend the time to strictly memorize them note card-wise, that's fine, but it's not a big deal to stress about. And as far as the different variations of the periodic table, it's the same periodic table. We just highlight different sections of it. So some of that can become helpful, some of it not. The other one that I would say you remember is that intersection is your transition elements. All right, so that's really only 3 that I would say really super important that you should recognize those names. Transition elements, halogens, noble gases. Okay. The rest, you will see people reference. In my opinion, it seems to be the older the chemist, the more they rely on these names for classifications. Okay. You've got the lanthanides and actinides referred to as the inner transition elements, because if you look really carefully, both on our table and here, this one actually gives you a little indent here. This section, that bottom section, is actually supposed to inlay inside, just like the transition elements inlays inside the other 2. Okay. So one version of the periodic table you might see is one big, giant, long stream where this guy is in the middle. Okay. Why do we not do that?
Doesn't look good.
Because then it's one big, long, giant streamer, and it seems to make a little bit more sense to offset it like this. Okay. It's just kind of a visual cue for it. So there are our names. We got our group 1. And actually, I got to address one more thing here. Okay, your vertical columns are your families or groups. Absolutely, you do need to recognize that. You don't need to know necessarily what the name is, but group and family is important to recognize as your vertical column. The horizontal row is your period or series. The two most commons that you'll hear would be period and I think family are actually the two most common terms that pop out. Okay? The common names for each of your groups. Group 1, that's that first column, are your alkali metals, alkaline earth. They're your nitrogens, chalcogens, and halogens. The only reason why I remember the nitrogens and chalcogens is because I think it's fun to say. So because we've wandered off topic as far as we can already, let's go ahead and do it all together. Ready? 1, 2, 3. It's kind of fun to say, isn't it? So now you'll remember your nitrogens with nitrogen. There you go. Okay, and I'm not actually sure. I just make it up each time.
Do you need to memorize that?
You do not need to memorize those two. Okay, so what can we do with this from Mendeleev's abilities? Okay, so what can we predict about francium? Okay, as you might guess, francium is in that giant gray bar. Okay, but if you didn't know, we could take a look at the periodic table. Francium has the symbol Fr. Okay. And if we're now going to try and take a look at this, we can compare what's happening. Wait a second. It's because it's not supposed to be francium. I was like, that doesn't make sense. Francium doesn't belong there. We have potassium. Let's try that again. I was like, we could predict francium. That's fine. But potassium's a little more interesting. What can we predict about potassium? Okay, we could go through and say its element letter is K. That's not predicting.
It's an alkaline metal.
We could say it's an alkaline metal, which also happens. Is it alkaline? No, it's alkali metal.
Predict its melting point's around 50 Celsius.
We could look at the melting point. If you take a look at the melting points within that family, you got lithium, sodium, then it would be potassium, rubidium, cesium. So if we take a look at the melting points, what happens to the melting points? They drop. So as a rough approximation, what might we guess for the melting point of potassium? Okay, you're going to guess somewhere about 50. Okay, reasonable guess. Would 100 be a reasonable guess? No. How about 28?
Sure.
No, because it's too low. Okay, so we're looking at something sandwiching in between those. Could we make a prediction about the atomic mass? What would our prediction on the atomic mass be?
39.1.
That's using our periodic table. That does not count.
70?
Okay. Why'd you pick 70?
I don't know. Just made sense.
Okay. What does our periodic table, or what does our trends give us? What happens to the atomic mass as we move down the column? It increases. So if we go from 7 to 22, skip something to 85, we would expect whatever that was skipped should have a mass between 22 and 85. Okay? What the exact value is not actually relevant to the discussion. But realizing that it has to be somewhere in between there is your valid interpretation. It's looking at a pattern and saying this section is missing out of the pattern. More than likely, it needs to be this. It needs to fit within that pattern scheme. This is an important aspect of science in general. And you may look at it, oh, haha, that's funny. That's fine. That's up to you. But this is what you're trying to do in a science class, is look for that pattern, identify a pattern, and make a reasonable guess. What happens when we look at the density? So we might be looking at 1.2 something. Why? What's the difference above? Roughly 0.5. What's the difference here? roughly 0.4, 0.3. I think it's closer to 0.4. So that difference is decreasing slightly, but we're probably looking at somewhere where we're adding roughly 0.5. Whoops, not 0.5. Oh, wow, yeah, this one does get a little bit weird. We're trying to add something that's going to set us somewhere in between those two values. Right? And we might guess it's adding 1 or 0.5. But if we guess that, that puts us higher than the next ones. Okay, so we probably want to go a little bit lower than that. Maybe say it's 1.2. All we're trying to do is pick a value that sits in between that, that matches that trend as best as we can possibly predict. Okay? Atomic radius, same deal. We're just trying to pick something that sandwiches between that. Does that mean all of our answers are correct? No. Particularly interesting one would be our density actually dropped. Okay. Is that relevant to the question that's asked? No. You took a guess based off the data that you had. Use that information as a solid guess. You have an explanation for why you pick that. It's a hypothesis. We can then test it. What happens, as with most science?
Failure.
It fails. So then what do you have to do? You'd have to come up with a new explanation of it. That new explanation is going to be beyond the scope of this classroom, so we don't need to worry about that. But what you do need to be able to do is come up with a prediction or a guess of what you would expect out of those. To be able to ask this question on the exam, I have to give you a lot of information. Okay? I expect you to be able to do these interpretations. Questions? Take a look at the practice exam. You tell me. Given the above information, which of the following is a reasonable density for potassium? And by above information, we should really cross that out.
A or B, that should be acceptable, right?
Where is A as a value? It is lower than that of sodium, whereas all the other ones go higher. So A doesn't make sense because that doesn't match our trend. B does go higher. Why not C? It goes too high. Okay. So our answer in this case is B. Are we right? Who cares? Based off the information we've got, that's what we have to use. Okay? Chemical properties, we can do a similar thing with chemical properties and how they react with oxygen. So a nice simple question that we could ask from the exam. What's the formula for the chloride of calcium? Sorry, the formula for chloride of calcium is CaCl2. What is the formula for the chloride of barium? What do we need to know to answer this question? Periodic symbols. We need to know that the symbol for barium is Ba. Now what can we do? Go to the periodic table. Where is barium on the periodic table? 56. Okay, based on that information alone, the formula for chloride for barium is completely out of our grasp. So what other information do we need to know? We could go to charge, but we don't know charge yet.
It's in the alkaline,
It's in the same family as the other one.
I don't care what the name of the family is. What I care is that it's in the same one as calcium chloride, or the same one as calcium. And calcium, when it reacts with chloride, reacts according to this formula. 2 chlorides for every calcium. Well, what did we say about the reactivity within a family? It's the same, which means the formula that I would expect for barium chloride would be BaCl2, because it matches the data given. That's what you need to be focusing on. Yes?
Is this affected by the group numbers up top as well, that also differences?
Yes. No. Not really. Individual periodic trends. So we get lots of trends coming off of this. We're going to address atomic radius now. And we'll address it again on Tuesday. So we find that there are two trends for atomic radii. Okay, the first one I think makes sense. Atomic radius decreases as you go up a group. What's changing when we move up a group? Or down a group for that matter. So let's pick hydrogen. What happens when I go from hydrogen to lithium? What did I do?
Increase the mass.
How do I increase the mass?
You didn't do it, science did it.
How do we increase the mass? Adding more pieces to it. More protons, more neutrons. But our protons and neutrons are located where? In a superdense nucleus, which if we compared our nucleus to the atom, the nucleus is a marble and our atom is the superdome. What's contributing to the superdome? If it's not the protons and the neutrons, it's got to be the electrons. What happens as you go from hydrogen to lithium? More electrons. What happens as you go from lithium to sodium? More electrons. Sodium to potassium. Potassium to francium. More electrons. As we add more electrons, what's going to happen? It should necessarily get bigger. Okay? Because we can't put the same electrons into the same space, because what happens when an electron gets near an electron? They repel away. So we end up having to put those electrons further from the nucleus each time. So our atom gets bigger as we go down. As we go down, it gets bigger. What happens as we go left to right, as we move across a period? So we move from, say, boron to carbon. What happened? Increased what? Electrons, right? More electrons. We move from carbon to nitrogen. More electrons. What should happen to the size? Should get bigger. What's the trend? It gets smaller. That's really weird. That really weird observation has to do with where electrons can exist. So now we jump back to chapter 4 to talk about where electrons can exist. Once we know where electrons can exist, the periodic trend of atomic radius makes sense. Yeah.